Welcome to our exploration of the biomechanics of human bone. In this video, we'll dive into how the unique composition and structure of bone allow it to withstand the mechanical loads we encounter every day. From supporting our bodies to enabling movement, bones are much more than just rigid structures. They are dynamic, living tissues that adapt and respond to the forces placed upon them. By the end of this journey, you'll have a deeper appreciation for the remarkable engineering behind our skeletal system and how it keeps us moving, protected, and strong. Bones serve several crucial mechanical functions in the human body. They provide a rigid skeletal framework that supports and protects our vital organs and tissues. But bones do more than just shield, they also act as levers, allowing our muscles to generate movement. When muscles contract, they pull on bones, which rotate around joints, enabling us to walk, run, lift, and perform countless other actions. This lever system is fundamental to all our movements, making bones essential for both stability and mobility. Let's take a closer look at how bones function as levers. A lever is a rigid object that rotates around an axis when a force is applied. In our bodies, bones act as these levers, with joints serving as the axes. Muscles attach to bones, and when they contract, they generate forces that move the bones. This system allows us to perform complex movements with efficiency and precision. Without this lever mechanism, even simple actions like picking up an object would be impossible. This image illustrates the concept of bones as levers in the human body. Notice how the bones are positioned to rotate around joints, with muscles applying force to create movement. This arrangement is what allows us to perform a wide range of actions, from the delicate motions of our fingers to the powerful strides of our legs. Understanding this lever system is key to appreciating the mechanical sophistication of our skeletal structure. Now let's define two important concepts: stiffness and compressive strength. Stiffness refers to how much a material resists changing shape when a force is applied. In bones, it's the ratio of stress to strain, basically how much force is needed to deform the bone. Compressive strength, on the other hand, is the bone's ability to resist being squeezed or compressed. It's the maximum load a bone can handle before it deforms or breaks. These properties are crucial for bones to support our weight and withstand everyday forces. Stiffness and compressive strength of bones come from their mineral content. Two key minerals, calcium carbonate and calcium phosphate, are responsible for making bones rigid and strong. These minerals form a dense matrix within the bone, allowing it to resist deformation and withstand heavy loads. Without adequate mineralization, bones would be too flexible and unable to support the body's weight or protect vital organs effectively. While minerals give bones their stiffness, collagen provides flexibility and tensile strength. Collagen is a protein that acts like scaffolding within the bone, allowing it to bend slightly without breaking. This flexibility is vital because it helps bones absorb impact and resist forces that might otherwise cause fractures. As we age, however, collagen content decreases, making bones more brittle and prone to breaking. Collagen is the most abundant protein in the human body, serving as the scaffolding that gives strength and structure to bones, skin, cartilage, and tendons. Recent advances in medical science have leveraged collagen in innovative ways, from healing scaffolds and 3D bioprinting to stem cell therapies and synthetic implants. These breakthroughs are transforming everything from wound healing to bone and joint regeneration, highlighting collagen's critical role in both health and medicine. Water is another important factor in bone strength. It makes up about 25 to 30% of bone weight. This water content helps maintain the bone's flexibility and resilience, allowing it to absorb shocks and adapt to different forces. Along with minerals and collagen, water ensures that bones are not only strong, but also able to withstand the stresses of daily life without becoming brittle or easily damaged. Bone porosity refers to the amount of bone volume filled with pores or cavities. This characteristic significantly affects bone strength. Bones with higher porosity are lighter and can absorb more strain, while those with lower porosity are denser and stronger. The balance between porosity and density is essential for bones to function effectively, providing both strength and the ability to withstand impacts. There are two main types of bone tissue based on porosity: cortical bone and trabecular bone. Cortical bone is dense and compact, found mainly in the shafts of long bones. It is low porosity, making it very strong and able to withstand high stress. Trabecular bone, also known as cancellous bone, is spongier and found at the ends of long bones and in the vertebrae. Its high porosity allows it to absorb more strain and distribute loads more evenly. At the microscopic level, bone is organized into structures called osteons, especially in cortical bone. Osteons are cylindrical units that run parallel to the bone's long axis, surrounding central havrecy and canals. These structures help distribute nutrients and resist mechanical stress. The arrangement of osteons is a key reason why bones can handle various forces without breaking down easily. This image shows the difference between cortical and trabecular bone. Cortical bone forms the dense outer layer, providing strength and protection, while trabecular bone fills the interior with a spongy lattice-like structure. This combination allows bones to be both strong and lightweight, optimizing their mechanical performance for daily activities and sudden impacts. Here we see a digital representation of a cross-section of a long bone. The dense cortical bone surrounds the spongy trabecular bone, creating a strong yet flexible structure. This arrangement is essential for withstanding the various stresses bones encounter, from supporting body weight to absorbing shocks during movement. Cortical bone is stiffer than trabecular bone, which means it can withstand more stress but less strain before breaking. In contrast, trabecular bone is spongier and can undergo more deformation before fracturing. This difference is crucial for how bones handle different types of forces. Cortical bone provides strength, while trabecular bone offers shock absorption and flexibility. Bones are anisotropic, meaning their strength and stiffness vary depending on the direction of the applied force. This property allows bones to adapt to different types of loads, whether it's compression, tension, or shear. The anisotropic nature of bone is a key reason why our skeleton can handle the complex and varied forces we experience every day. Bone is strongest when resisting compression, forces that push it together. It's weaker when resisting shear, which are forces that slide one part of the bone against another. This directional strength is why bones are more likely to break from twisting or bending forces than from straight compression. Understanding this helps explain why certain injuries occur more frequently and how bones are designed to handle everyday stresses. This image helps us visualize how bone strength varies with different types of forces. Notice how the bone structure is optimized to resist compression, while areas exposed to shear are more vulnerable. This visualization underscores the importance of bone architecture in maintaining skeletal integrity and preventing fractures. As we age, our bones lose collagen, which increases their brittleness. This makes older adults more susceptible to fractures, especially from falls or sudden impacts. Maintaining bone health through proper nutrition, exercise, and medical care is essential for reducing the risk of osteoporosis and other bone-related conditions. Exciting advances in biomaterials, 3D bioprinting, and stem cell therapies are revolutionizing bone regeneration. Collagen-based scaffolds and synthetic implants are now being used to repair and replace damaged bone tissue. These innovations hold great promise for treating injuries, degenerative diseases, and even enabling organ regeneration in the future. Summary: human bone is a marvel of natural engineering. Its unique combination of minerals, collagen, water, and specialized structures allows it to support, protect, and move our bodies with remarkable efficiency. Understanding the biomechanics of bone not only deepens our appreciation for the human body, but also guides advances in medicine and technology. Thanks for joining us on this journey through the secrets of bone strength and structure.